Welcome back, guys. Let's continue using this new method, the Lagrange multipliers, to find this time the minimum value of the function f subject to the given constraint. So remember, the first step is to identify what is being optimized. That's our f function. And what is the constraint? Making sure that it's a function equal to a constant. The function side is g. So in this case, g is a function of both x and y, and it's equal to x plus 2y. Now that we know what f and g are, we can find their gradients. So gradient of f is equal to 2x minus 2, comma 8y plus 8. Gradient of g would be equal to 1, comma 2. So now we can set up our system that comes from gradient f equal to lambda gradient g. In other words, we have the vector 2x minus 2, comma 8y plus 8 is equal to lambda times 1, comma 2. And then we'll break that down into the components. So we have the I hat component, which would look like 2x minus 2 equals lambda, and the j hat component, which looks like 8y plus 8 equals 2 lambda. We do have 3 unknowns, so in order for us to create a system that has a real solution, we need to make sure to include the constraint. And now this set of equations will help us solve the problem. It will help us find the minimum value of our function, making sure that we pick a point, x and y, that satisfies our constraint. So looking at these 3 equations, we want to be clever about how we solve this system. We would ideally love to shrink this down to one equation with one unknown. So we can do substitution if we'd like, and try to reduce this down to one equation with one variable. There's many ways to do this, but let's try this technique. Let's look at the second equation, solve it for lambda. So 8y plus 8 equals 2 lambda. That's actually the same thing as lambda equals 4y plus 4. And then we can substitute that lambda into the first equation. So that would look like 2x minus 2 equals this version of lambda, 4y plus 4. Every term in this equation has a factor of 2 in it, so let's start off by dividing by 2. We get x minus 1 equals 2y plus 2. And then we can simplify this so that we can see that we have x is equal to 2y plus 3. So this is giving us a relationship between x and y. We went from x, y, and lambda down to x and y. We're going to use this with the third equation here so that we can find a value for x. So we have x plus 2y equals 7, and we also have x, I'm going to write this as minus 2y equals 3. Using elimination, I can add these 2 equations together to get 2x. The y's cancel out, equals 10, so we're able to find x equals 5. Notice here, we did not find any value for lambda. Instead, we just used lambda as a stepping stone to find a value for x. Now that we have this value for x, we can try to find what y would have to be. Now be careful, if you substitute this back into the wrong equation, you're maybe going to find something that depends on lambda. But if you substitute this into the third equation, you will find something that only depends on x and y. So plugging x equals 5 into x plus 2y equals 7, we get 5 plus 2y equals 7, or we get 2y is equal to 2, or that y equals 1. So we found one solution that occurs at 5, 1. In fact, in this case, it's the only solution. This was a much more straightforward system of equations to solve. Now we just pop that into our function, f of x, y, using 5 for x, 1 for y, to find what the minimum value of our function is. And we get 27. So the minimum value of our function is 27. Subject to Now you might wonder, how do I know this is a minimum? Nothing in this tested that point for a max or a min, like how we use the second derivative test. Well, with the method of Lagrange multipliers, since we're looking for absolute max and min, because we have this constraint, all you would need to do is test your function for other values to see if the function spits out bigger or smaller values. In fact, if you plug other points into your function, you'll find that every other point you can think of to plug in will spit out a value larger than 27. So you're not going to use the second derivative test on Lagrange multiplier problems. Instead, you would just evaluate your function at other points to test and see what's larger or smaller. Let's go back to that problem that we started with when I first showed you how the method of Lagrange multipliers works. The solution for this problem, let's work on it. So we're trying to minimize the function, which is the sphere, the distance to the origin, subject to the constraint of this cylinder. So our f is sphere, which means our gradient f is going to look like 2x, 2y, 2z. And our constraint, notice that we have a function equal to a constant. So our g function looks like x squared minus z squared minus 1. And that minus 1 can be on either side. It doesn't matter. In fact, with your constraint equations, you can always move every term over to one side and consider 0 on the opposite side as your constant. That's fine. You just can't have variables on both sides of the equal sign. If that's what's going on, then you got to move everybody over. All right, so if g is the left side of this constraint equation, then gradient g, the partial with respect to x, looks like 2x. The partial with respect to y looks like 0. There is no y in this equation. The partial with respect to z looks like negative 2z. From here, we will start our system of equations by setting up gradient f is equal to lambda gradient g and separating those into the components. So the I hat component from gradient f is 2x. And then from lambda gradient g, that would look like lambda 2x. The j hat component from from gradient f is 2y. From lambda gradient g is lambda times 0. And then the k hat component from gradient f looks like 2z. And from lambda gradient g looks like negative 2 lambda z. We do have 4 unknowns, but only 3 equations, so we have to add that constraint equation back in. And then we can solve this system. So we have 4 unknowns, 4 equations, perfect. From here, we can probably see that there's a few things that simplify. For example, if you have 2 on both sides of your equations, you can divide it off. Be careful about dividing the x off, though, because who knows? X could be equal to 0. Lambda times 0, this equation is just equal to 0. We've got 2's on both sides we can divide off. So let's rewrite our system so it's a little cleaner. So we have x equals lambda x. We have 2y equals 0. In other words, let's write that as just y has to be equal to 0. We have z equals negative lambda z, and then we have x squared minus z squared minus 1 equals 0. To solve this system, we're going to have to examine multiple cases, just like the first time we used this method of Lagrange multipliers. So let's take a look at our first equation, x equals lambda x. We have two possibilities. Either x equals 0 or it does not. If x equals 0, the equation is satisfied. If x does not equal 0, then we can divide it on both sides so that we get x equals lambda x, divide x on both sides. We find lambda has to be equal to 1. So we have possibility number 1, x equals 0. Possibility number 2, x does not equal 0, but instead lambda equals 1. The y equals 0 equation doesn't give us any new information. We know y has to be equal to 0. The next equation, z equals negative lambda z. We have two possibilities. Either z equals 0 or it does not. If z equals 0, the equation is satisfied. If z does not equal 0, then we can do the same thing we did in the x equation. Divide both sides by z. We get negative lambda equals 1, or rather that lambda equals negative 1. So we have a third case and a fourth case. 3 is that z equals 0. And the fourth case would be that z does not equal 0, but that lambda equals negative 1. Now we're going to go back and plug each of our points into our constraint to see what the other values would have to be. Keep in mind that y has to be 0, so for any one of these possibilities, we can copy over that y has to be 0. That doesn't even play a role in the constraint though, so it doesn't really give us much more in the direction of a solution. But if x equals 0, y equals 0, and then we look at our constraint equation, we would see x equals 0 would give us 0 squared minus z squared minus 1 equals 0, or rather that z squared equals negative 1. And if we tried to square root both sides, we'd find that this is an imaginary case, so no real solution, only imaginaries. So we'll ignore that case because we're looking for real points that exist in the XYZ coordinate system. Moving on to our second option, where x is not equal to 0, y is equal to 0, and lambda is equal to 1. We would plug that into our system and we would see x equals x, which is good news, y equals 0, obviously, and then z equals negative lambda, or negative 1, times z. And the only way for this to be true would be to imply that z equals 0. So we have x equals x, y equals 0, z equals 0. And then we would plug that into our constraint. If x equals x, then we have x squared minus z equals 0, minus 0 squared, minus 1 equals 0. And that simplifies to say x squared equals 1, or x equals plus or minus 1. This is actually our solution. We have x equals positive 1, y equals 0, z equals 0. And then we also have the case where x equals negative 1, y equals 0, z equals 0. And if we were to try and figure out what happens in cases 3 and 4, I'm going to spoil this for you, but I encourage you to try this on your own. You would find the same thing. If z is 0, y is 0, go through your work, you'd find that x has to be plus or minus 1. And then in the fourth case, even if lambda is equal to negative 1, you would be able to, oh, no, this one won't work. Actually, I forgot that fourth case has z cannot be 0. So the fourth case would come out to be bogus. Case number 3 would match case number 2. And case number 1 turned out to be bogus. And if we look at our picture, if the red axis is the x-axis, x equals +1 would be here, x equals -1 would be here. Notice that those points are on the x-axis, so y would have to be 0, and so would z. So those are the points that are closest to the origin. Now, unlike the last problem, this question does not ask us to find the value, the minimum value of the function. It does specifically say find the points. So for this problem, our answer would be these 2 points. These points are closest to the origin. And we would be done.